Okay, so I'm Cindy, and as she said, I'm currently earning my degree in environmental sciences here at UCR, and I'm here to share with you the preliminary results of a project I've been assisting on that was developed by Yang Li, who is here today. So before I get started, I'm going to give a brief background on energy consumption and introduce you to waste-to-energy systems, as well as the unique components of our experiment. Then I will interpret our results and touch on some possible future modifications. So our country is dependent on fossil fuels. In 2010, 83% of the total energy consumption in the United States was from fossil fuels. This includes petroleum, coal, and natural gas. Only 8% was from renewable energy sources. And I'm an advocate for sustainable energy, but these sources aren't proving to be a viable solution right now. And with the increase of concern for oil depletion, we need to start making the life cycle for gasoline more efficient. And that's what this project is designed to do. So the life cycle analysis for petroleum or gasoline is commonly referred to as well-to-wheel. Here you can follow petroleum's life cycle from when it's underneath the Earth's crust to when we pump it into our cars and emit it as greenhouse gases. So what our Fischer-Tropsch reactor is designed to do is eliminate the need for oil extraction and several stages of refinery. Not only are we removing these environmental degrading and costly practices, but we are replacing the source with something renewable. In our case, municipal solid waste, which I'm sure everyone here calls trash. But you can't just go trash to gasoline or waste to energy. It requires certain processes. CE-CERT has designed its own waste-to-energy system to meet this need. You start with your feedstock, such as trash, and expose it to high temperatures and high pressure in the presence of water, and this gasifies it into methane with the presence of water. These products are then put through another reaction and transformed into carbon monoxide and hydrogen gas. These are the two gases that we used in our Fischer-Tropsch reactor to produce gasoline. So in the laboratory setting, we use tanks of carbon monoxide and hydrogen, but in reality, it would be our reactor could handle the fumes that came from the entire process. The lower picture is just showing some of the control devices that we needed, such as a carbon monoxide monitor and a flow rate control. These gray boxes read different data that the reactor generated and sends it to computer program that I'll explain later, but first let me define Fischer-Tropsch synthesis. So Fischer-Tropsch starts with carbon monoxide and hydrogen gas and synthesizes it into hydrocarbons. Predominantly 40% of the products fall within the gasoline range. Now, just because they're in the gasoline range doesn't mean that these hydrocarbons are of high enough quality to meet the fuel grade standard to put into pump stations. So our project is trying to increase the percentage of gasoline hydrocarbons from Fischer-Tropsch, as well as produce higher quality gasoline. How we're doing this is by introducing a novel catalyst into the reactor, specifically ZSM-5, which is an aluminosilicate zeolite catalyst that has the ability to break down heavy hydrocarbons. In doing this, it ideally confines the hydrocarbon production within that gasoline range of C5 through C12. Here's a better comparison of the conventional Fischer-Tropsch catalyst, which produces hydrocarbons in a wide range, and those products require further processing in order to be used in our fuel tanks. And then the new catalyst with the zeolite shell, and you can notice the pores on it, and those pores are what allow the products to escape. But because of the pore size, it confines it to only being within that gasoline range. So what we did was take these catalysts and put them into our reactor. We used a fixed bed reactor, which Yang set up and secured in one location to protect it from the elements. Fischer-Tropsch is a strong exothermic reaction, which means it releases a lot of heat, and even the smallest slight of wind could cause the temperature to fluctuate, which if the temperature were to change too dramatically, then it would ruin our entire experiment and we would have to start over. So a basic PID control program was developed to automatically kind of regulate the small fluctuations in temperature. So as I said, it's a strong exothermic reaction. We didn't just start it off at 220 degrees Celsius. It actually started at 170, and then over the time span of a couple of days, slowly increased the temperature to the reaction time. So this is a screenshot of the PID control that we used. This is us increasing the temperature over a couple of days, and as you on both sides of it, the slope interval is kind of a constant slope interval, which is ideal for this type of reaction. In the center, you can notice that the temperature starts to peak. These two lines represent the catalyst temperature and the reaction temperature, which was the two most important factors of our experiment. And so as the temperature began to increase, the PID control kicked in and was able to correct it. And then again, it starts to increase, but it automatically corrects it by, for those of you who don't know PID control, it looks at the past and present to predict the future and kind of uses all three components to determine how best to control the reaction. So sometimes the PID control wasn't enough, and we did have to manually make a few changes to control the temperature. Because like I said, if the temperature were to run away, then our experiment would be ruined and we wouldn't get any results. But luckily, we were able to successfully maintain the optimal operating level for the Fischer-Tropsch. And so first, we ran the conventional Fischer-Tropsch catalyst. And this is a picture of the results that we got. So typical Fischer-Tropsch, you get a large range of hydrocarbons